Welcome back to another AP Pre-Calculus video. Today we'll be going over topic 2.11 on log functions. The first thing on this topic is knowing what the functions will look like based on what we see. So like the first numbers, is it a positive or negative, and based on that, then the function, as we can see like down here, it's going up or going down, or it's like concave up or concave down. So yeah. If you remember from the 2.11 notes, I'll have that up, screenshot, that A is our first number right here. All of those are A. Also for your information, getting this file took away like the equal signs and parentheses, so that's why it looks like that. Yeah.
Bruh.
Anyways, so if our A ends up being greater than 0, then the graph will look like that. It looks like it's starting from a negative and then going to positive. So it's increasing. The graph is increasing, but it's concave down. As you can see, if we extend it to look like a U, and it's going to look like an upside down U, which is concave down. And then the graph on the right, if our number is less than 0, which is a negative number, then the graph will be decreasing, but it's concave up. If we extend that letter U, it will be a upright letter U. So that's concave up. Well, obviously, the concaves, like concave down, is on the graph on the left. Concave down means that the rate of change is decreasing, because we can see the left side of the graph closer to the y-axis. It's like very steep going up. If it's very steep going up, that means it's positive and a very high slope. But then we see it's starting to reach a slope of 0. A slope of 0 is like straight horizontal line. So yeah, that's decreasing. The rate of change is decreasing there. Then we have concave up. The rate of change is increasing, even though the graph is decreasing, because we can see the left side of the graph, the one closer to the y-axis, it's very steep, but it's going down. So it's a very high slope, but negative. So that's, yeah. And then we can see as the graph keeps on decreasing, the slope is changing. It's getting less steep, so it's getting closer to 0. That means that the number's increasing. It's negative to 0. So think of a number line. It's going from a negative number to 0. That means it's increasing. So yeah, I was just explaining the graphs a little bit more, and how you can distinguish those two. So let's go ahead and get started. Hopefully you remember how to write limits here. So yeah, so we can see here that our number is 3, and 3 is greater than 0. So that means our graph is going to be increasing, not the rate of change increasing, but the graph will be increasing. So that's our x and y, and then our graph is going to start from negative and go up to positive. I should do that a different color, so there, like that. So we can write our limits as x. So this is, you just have to remember that you're writing it like this. On the left side, it's going to be 0 from the right, and then our equation, then that's equals, it's going to right here, as we get to 0 from the right, we see that y is going to negative infinity, so it's negative infinity. And on the right side, we're always going to be writing positive infinity. So yeah, this is the left side of the graph, this is the right side of the graph. So when x is going to positive infinity here, this is infinity, we see y keeps going up, so y is also going to positive infinity. So f of x is equal to positive infinity. So now the next one, we see this is a negative number. Negative 2 is less than 0. So that means we know our graph will be decreasing. So it's going to look like, it's going to start from positive and then go down to negative. So the limit for x will always be the same. So x, as it goes to 0, from the right, as it goes to 0, it looks like y, or a g of x for this one, g of x is going to positive infinity. So infinity, I just write infinity. You can put a positive sign if you want, but yeah. And then for the right side, as x goes to positive infinity, because it's It's always going to positive infinity no matter what on the right side. Yeah, so log graphs always have the characteristics of x is always doing the same thing. The left is reaching 0, and then the right is reaching positive infinity. That's why it's always the same here. But then y always changes, because we don't know if the graph is like decreasing or increasing. So on the right side we see it's going to negative infinity. What am I doing? But that's negative infinity, so yeah. And now our last one is 3/4. It's not a negative number, so that is 3/4 is indeed greater than 0. If we write our small graph, it will be negative to positive, so it's increasing. So we know that the y on the left side is going to negative infinity as x goes to 0. H of x is going to negative infinity, and then on the right side, as x goes to positive infinity, h of x reaches positive infinity to infinity or positive infinity, whatever you prefer. I did both, I guess. Alright, so our next question, we have a set of questions here. So each graph is going to have 4 questions contained with them. So our first one is a graph of k of x. We see that the graph is decreasing. Okay, and it's also saying rate. And just so you remember, rate is the same thing as rate of change or slope. And like we talked about earlier, we see that this is a very steep slope going down. So that means it's negative. And it's reaching a constant slope or 0. So that means it's increasing. From a number line, we have a negative. Let's say -5. And then 0 is here. That is increasing because numbers go from left to right. Like, I never knew that. Graph is decreasing, so I'll just write that. Decreasing. But it is, ROC is increasing. So then, we'll look for one that says decreasing at an increasing rate. We can already cross out A and B because that says increasing. The graph is not increasing. We see C says decreasing at an increasing rate. Yeah, that's correct. So our answer is C for that one. Alright, so our next one. Which of the following pairs of the limit statements correctly describes the end behavior of K? So let's look at it on our own first. We see as x is going to 0. On the left side of the graph here, y is going to positive infinity, okay? And then as x goes to positive infinity on the right side, y is going to negative infinity, okay? So we'll find one that says infinity first for the left and negative infinity for the right. So we see these two have negative infinity for the left, so they're wrong. Probably do it in red. They're wrong. Positive infinity, this is negative infinity, so C is our answer there. Alright, and so 6, which we'll find could be the equation for K. So we're looking for the equation here. So we know this equation is decreasing, so when we remember, of course we had to have memorized that, so decreasing, that must mean that A is less than 0. I mean, that's pretty easy to remember. If it's decreasing, then it's a negative number or less than 0, and if the graph is increasing, then the number is greater than 0 or it's positive. So we know our A has to be negative. So when we look at this, we see these two are negatives, A and C are negative. So we can cross out B and D because they're positive. Cross B and D out. And so we're talking about log graphs here. So clearly C is not correct because this right here is oh, why is it not working? It's not working. Finally. We can see that because this is exponential. It's an exponential graph. As we remember, our format of the graph from like 2.9, I believe, exponential is b to the power of a is equal to c, and log is log b times c is equal to a. We see here there's no word of log there, so like this just can't be. Our answer can't be C because we're talking about log graphs here. Unfortunately, we do know because the title says log functions. So our answer would be A. We can cross out C and it's A. And so yeah, exponential graphs would not look like this too. So yeah. So now number 7, which of the following equations could be k negative 1, which is the inverse of k of x. So we're trying to find the inverse. And as we remember, to find the inverse, we need to replace x and y. And we know our equation here, so that's easy. This is our equation, so we're going to use that. I did erase some questions we're going to do later to give us space to write down here, but I'll just bring it back later. So we're changing our equation we know up here, so I'm going to put it down here. So that's our equation. I just replaced k of x with y because that's basically y, right? And we know we're replacing x and y, so we need to do that. Now we can put now we can replace the x and y. X is equal to negative 2 log 4 times y right here. So now what we want to do is isolate y, so we figure out what the equation is, because an equation has to be y is equal to, right? So we're isolating y. We know we can't really do anything with a log right now, so we can divide each side by 2 to get rid of that. So x divided by negative 2 is equal to log 4 times y. So now, I think it would make it easier if we change this back into, if we change this to an exponential form. We know this is equal to b right here, and this is c, and this whole thing is a. So when we change it, we have, and we're only doing this so we have 4, an exponential, remember, exponential is b times a is equal to c. So we have 4 to the power of x divided by 2 is equal to y. So we can get rid of log because we know we're finding the inverse of this equation, and opposite of log is exponential. I should have said that earlier, but yeah, when we're it's always the inverse. These two, they're always the inverse of each other. So yeah, let's go back to the equation here. So now we know y is equal to that, but we can further simplify this. So we know this right here. We can separate. So we can do 4 to the power of negative 1/2. Also to the power of x is equal to y. So now we're doing this. And then remember, when we are doing to the power of a negative number, we have to put that into a fraction. So this would go into 4 to the power of 1/2. So the exponent is positive, and that's all under 1. So that's our fraction. This would change into 2 because it is basically equal to the square root of 4. Because remember, the denominator is the index number, and the numerator is the exponent on the inside or the outside. And 4 to the power of 1 is 4, so that works. So yeah, this is equal to 2. So 1/2. And so if we're rewriting this entire thing, if this is equal to 1/2, then it's 1/2 to the power of x is equal to y, but we don't want to write y, we want to write the inverse, and we know we used k of x, so it's k negative 1 of x. So that should be our answer. And now let's look into the answer choices. We can already scratch off C and A, or D, because they contain log. And an inverse of a log equation is not log. It has to be exponential. We see A looks like our equation, so the answer is A. So now moving on to the next one. We have the graph of M. We see it is increasing, and then we see positive, and then it goes to 0. So it is decreasing. ROC is decreasing. Okay, so then we find that in our answer choices. Increasing, we can cross out C and D. That says decreasing, so it's increasing at a decreasing rate, so our answer is B. So now to find the limit statements, we have, let's see, on the left side, when x is reaching 0, we see y is going to negative infinity. So it has to be these two, so we can cross off C and D. And then we see as y or x is going to positive on the right side of the graph. We see y is going to positive infinity. This is negative infinity. So it should be the right side limit should be going to positive infinity, and that is B. So our answer is B. All right. So now which of the following could be the equation for m of x? So we see our a should be, because this is increasing. So then we know that our a should be a positive. Easy to remember. If it's increasing, then our number should be positive. If it's decreasing, our number should be negative. So a is greater than 0. So our number should be positive. So we know it's not a and c because those are negative numbers. So now we look at this. We're looking for a log equation. So it's not D. So our answer is B. So now, which of the following equations could be the inverse for m, which is m negative 1 of x? So, using this equation up here, we want to switch the x and y. I'm going to write the original equation, and now we want to switch the x and y. X is equal to 3 log 8y. So now isolate, we can divide that 3. It's not part of the log because log is log BC. Yeah, that's the log is equal to A. And so x divided by 3 is equal to log 8y. Now we can change this into exponential form. This right here is A. This is B and this is C because log is log B times C is equal to A. And then we know exponential is BA is equal to C. So when we change this, it should be B to the power of A, which is 8 to the power of X over 3. Now is equal to C, and C is Y. Alright, so yeah, now we want to simplify that. So we can separate 1 over 3x. So a fraction, we have a fraction here. It's not negative, so we don't have to change it into another fraction. So we know that this is going to just be the same thing as the cube root of 8. Denominator goes into the index. You can add a 1 here if that makes you understand more. And then this is equal to 2, basically. So now it's just 2, because that's the cube root of 8 is 2. And don't forget to bring that to the power of x back in, and that's equal to x, or equal to y. So that should be our inverse equation right there. So when we look back, we know our inverse equation can't be log. So we can take that out. The rest seem to be exponential, so yes, that's correct. And the one that matches what we got, 2 to the power of x, is C. This one says a negative here. This one is 1 over 2. And those are incorrect. So C is our answer. And that's how you do that. Now I'm erasing all our work and C, and the equations behind it are coming back. So hopefully you got that work, because now it's all gone. So now we're doing these. So we're trying to solve for k. These are log functions, so we know that the x values should be changing proportionally, and not the y values. Usually the y values change proportionally, but that would mean that it is not a log graph. So we see that from this to this, it looks like it's multiplying by 10, because we see that the dot keeps changing, or the decimal place keeps changing. Why did I say dot? The decimal place is here. It's going there, which adds a 0 and gets it to 30. So that's also multiplying by 10. So if it's log, then all of it has to be multiplying by 10. So 30 times 10 gives us 300. You just add the 2 zeros. 3 times 1 is 3, and then add 2 zeros, or not add 0, 0 plus 0, 0. We see that there's 2 zeros, that means there's going to be 2 zeros in our answer. So k is equal to 300. Okay, our next one, 3 over 4, if it makes it easier, 3 over 4 is also 0.75, but that looks like 0.75. 3 divided by 0.75, we can do that, so 3 divided by 3 over 4. We can add 1 there. Sorry, this is divide. So we change it to multiplication. So we gotta switch that. So it's 4 over 3. So that equals to 12 over 3, which gives us 4. So that means 3 over 4. 3 over 4 times 4 is going to give us 3. So that means multiply by 4. So that means everything else is multiplied by 4 because it's a log graph. So 3 times 4 is going to give us 12. So k is equal to 12. So now 14 here looks kind of confusing on the y side, but we're going to ignore the y side because, again, the x side is what's changing proportionally. So let's ignore the k for now and just look at the coefficients. So we see 12 to 6, that's multiplied by 1/2, which is also the same thing as dividing by 2. Also multiplied by 1/2. So everything else should be multiplied by 1/2 times 1/2. Alright, so we can use one of the two x's together. So we would want to now use the two of them together, but we don't want to do these two because they both contain k, so we can't really solve for that. So we can do these two. We can have a variable. We're just going to equal it to 6 because we also have this right here. So now we multiply each side by 2. 3k is now equal to 12 divided by 3. So k is now equal to 4. That should be our answer. And if we look back, 3 times 4, that gives us 12. 6 times 4, that gives us 24. And then 12 times 4, that gives us 48. So yeah, that looks correct because each time it's dividing by 2. So now we have 15 here. Okay, we see we have exponents here. Seems like each of the exponent is always decreasing by 2 because 3 to the power of 3 gives us 27 here. And 3 to the power of 1 gives us 3. It can't be multiplying by 3 to the power of 2 though, because then it would be adding 2. Remember the exponent rule? So it must be 1 over 3 to the power of 2 then. So that when we multiply this, it is going to end up looking like 3 to the power of 7 over 3 to the power of 2, which that means that we're subtracting the exponents. 7 minus 2 is equal to 5, and that gives us 3 to the power of 5, which is this right here. So that looks correct. So it's probably the same for each of them. So 1 over 3 to the power of 2, 1 over 3 to the power of 2, and 1 over 3 to the power of 2. I'm going to keep the 3 to the power of 2. You can say 1 over 9, but it makes you understand more because then we know that we're subtracting 2 each time with the exponents. So now we have 3 times 1 over 3 to the power of 2. So we can add 1 here, and that gives us 9, which is 9 times 1 is 9, and then 3. So that's just 1/3. And if we look back and we know that exponent of the previous one is 1, and because it's 3 to the power of 1, 1 minus 2 is -1. So 3 to the power of -1 is going to give us that. Because remember, we want the exponent to be positive, so it's going to be 3 to the power of 1, and then it's under 1. So yeah, so that means k is equal to 1/3. Right, now our last thing to do is finding domain and range of function f. So we have function f here. Function f seems to already have transformations of its own, so we have to apply these transformations first before we apply these transformations. So for part A, it's telling us to find a domain and range of this. So apply these transformations. We see that remember it's the opposite, so it's going left 4. Think about a graph here. Starts at 0, so left 4, -4 here. So looks like our domain is -4 to infinity. Remember what log graphs are supposed to look like. So we know it's going to infinity. Domain's always going to infinity. But what about our range? Our range will always be the same. Our range will always be anything, because remember, our graph could be looking like this, or our graph could be looking like this. That means that it's going to all positive infinities and all the negative infinities. It's just going everywhere. So yeah, but the domain is what changes. So this number right here is, we don't care about that. So yeah. So now moving on to B, we see that it's negative here. So first of all, our number is positive, so we know that. Probably ignore this, but I'm gonna keep it there just in case you guys need to see it. We know that our graph is positive, so start from negative going to positive. So that's what ours looks like. But now that we have a negative number, so it reflected. So now it looks like that. So I'm gonna erase that. So that's what it looks like so far. That doesn't change the range, so I'm actually just gonna write the range here. It's just all real numbers. You can write all real numbers, but our domain, remember that it's at -4 right now after this, but now this has -3, so now we're gonna move it to the right 3 times. So we're at -4 right now. Say this is -4, right 3. So +3, -4 + 3, that gives us -1, which is right here. So our domain is -1 to infinity. So now C doesn't look like it's moving left or right, but it is multiplying by 2. That must mean that we had a dilation here. Remember dilation, it would be at x over b, whatever number we have. So that means if it ended up being 2, that means our dilation b must have been 1/2, because x divided by 1/2. You could change that to x over 1 times 2 over 1. That gives us 2x. So our dilation was 1/2. And because we know we weren't moving left or right anymore, we only moved left 4. I'm going to erase this right here. We know we're still at -4, but we have to do a horizontal dilation. So -4 times 1/2. That gives us -2. So now it's at -2. There's no other point we need to do a dilation because we know the range is all real numbers. So yeah, +7, we have +7 here, so the graph moved up 7, but that's not going to affect anything because the range is already, it already goes to both infinities, positive and negative infinity. So yeah, so domain is -2 to infinity. So that's how you do that. Hopefully that made a little bit of sense. You just need to know your transformations and understand how the log graphs work. So yeah, that's how you do 2.11, and hopefully that helped. Thank you for watching.